Hello, today I'm going to go over the project exam number 1 for spring of 2026. And it's going to be over the dynamic model for the poorly mixed tank. And I modeled the tank as two perfectly mixed regions because that's what it says to do. So for the first one, I have the volume as V1. So that's the energy balance one that I did with T1 as the temperature as well. And then I did the same exact thing for the second one. And then I had T2 as the outlet temperature. And then I have the feed enters at the flow rate Q and then temperature T in. And then for the second one, I have recycles back to tank one at flow rate QR. And then tank two receives heat from the coil through the term UA. And then I assumed constant density, constant heat capacity, constant volumes, no external heat loss. And then I wrote all of these assumptions here. And then for the first one, used the accumulation equals energy in minus out. And then the energy entering one comes from the fresh feed Q, T in, and the recycle stream. The energy leaving goes to tank two as the combined stream Q plus QR at temperature T1. And then after canceling rho Cp and as we can see, this is the final energy balance we get for the first one. And then we move to the energy balance for two, which is accumulation equals in minus out plus heat. And that heat's going to come from the coil, which was mentioned. And so for the second one, the inflow is the combined stream from the first, and then the outflow is the combined product plus minus stream at T2. And then the heat input at UA times TS and then minus T2. And so then that's how we get this. And then we go into steady state. And to get the steady state balances, I set both derivatives equal to 0. And then I define the deviation variables T1 prime and T2 prime, Tn prime and Ts prime by subtracting the steady state values. Using deviation variables was important to make sure that the transfer functions are defined most cleanly. And then for there, I rearranged the equation into the standard first order form, tau1 dt1 prime over d2, and then I wrote this all out, and then I defined everything here, which is how I got to that first order standard form. And then I did the same exact thing for the second one, put that back into the first order form again here. And then we took, or I guess I took the Laplace transformations with zero initial deviation conditions. That gave me 4 process blocks. And then in the diagram, I drew these all out here. And then from the Laplace, I took all of these, which matches to these 4 that you can see here. And then here are the equations to the block diagram. And there, we went down, we took the rate law, which allowed us to simplify everything down. And then that way we were able to rewrite everything, simplify that down, expand it out again once more. And then from there, I found the second order. And then from finding the second order from using the first equation and using the rate law or the loop law, I was able to then find the final second orders, which then simplified from the 4 blocks we found here from that initial first order that we found. And then this is the second order simplified block flow diagram, which matches with the project table that was used to find this. And then this is not showing any of the control just because we have not gone over that yet. And then we can see from the mapping table the process variables, the first order variables that came from that, then the second order ones, and the second order ones are the ones that are in the second block flow diagram, which is the simplified second order that we got to after we initially found that first order. And then that would be the block diagram for the first order. And then as we can see, we have these 4 blocks. We have the plus, and then we have the Tn, and then that goes to get the T1 prime of S, which makes sense based on our first order we found here, along with what exactly these all equal out to be. Same with the first order found for this problem.